Of the semester. And it's our great pleasure to have Dr. Alex Manda here from East Carolina University. Alex is actually from Zambia, but he went off and got his undergrad degree in geology from Cardiff University in Wales. Then he went to Florida International University to get an MS degree, and then finally UMass Amherst for his PhD. And you know some other folks who have attended UMass Amherst. Anyway, it's great to have him here talking about salinization. It's all yours, Alex.
Thank you very much. It's good to be here, and it's a pleasure to give a presentation on some of the work that we'll be doing in Eastern North Carolina. So the work that I'm going to present doesn't necessarily have an answer per se. So this is ongoing work, and this all started it's many years ago. I think in 2018, 2017 or 2019, when some folks from the North Carolina Cooperative Extension came to me and said that they were getting questions and incidences from farmers saying that the farmers were complaining about low yields in their fields. And in some cases, the phenomenon that they were describing was such that they would have these bare patches of land in their fields. And so you couldn't grow anything in those areas. And so they said, well, we kind of have a hunch of what's going on. We think that there's a lot of salt in these regions, and so they would get quite a number of pings across the eastern seaboard of the United States within North Carolina. And so here in this map, I'm showing some of the areas where farmers would complain. And so there's this one particular extension officer, Wood, who documented all these pings. And so in Eastern North Carolina, he is in the region where he's covering Pascagoula and Hyde counties. Those are sort of like close to Virginia, just south of the North Carolina-Virginia border. And so when we started to investigate, we found that indeed there was quite a bit of issues and concern from those farmers. And so we said, well, how can we explore this problem? On one hand, I'm a hydrogeologist, and then on the other hand, I'm working with these North Carolina Extension cooperative officers that are into soil science. But then the intersection is, water resources and water quality and provision of water to these farmers that they can use to grow their crops and grow their crops to a high degree. And so one of the things as a geologist was, well, what might be the potential source and where can we go to figure the answer to these questions? So for me, one of the major questions was, well, what is driving, saltwater intrusion or salinization? And how can we conduct some experiments to give us some answers to answer those questions? And so we then started to have interactions with farmers, and some farmers were willing to give us access to their fields to instrument them so that we could ultimately then run some experiments to determine what was going on. So ultimately we have 3 sites. There's Hyde County down here. Don't know if you can see my cursor, but close to the bottom of the slide. And then there's the 2 counties in the northeast, Pascagoula County and Camden County. And so those are the sites that we instrumented. So I'm going to describe later on what we did at those particular places. But one of the first things that we did, since I was working with collaborators from North Carolina State University in soil science and part of the North Carolina Cooperative Extension, we took samples of soil from 2 depths, 0 to 6 inches and 6 to 12. And so in the soil world, 0 to 6 is kind of like the shallow, and then 6 to 12 is kind of like the deep. So about a foot or so, but then half a foot and close to about a foot in depth. And so when we got those soil samples, we looked at two sites, and this is, I think, this is from Hyde County. And so at the Hyde County site, there was a location where it was normal, everything was growing as you'd expect, no problem. And then there was also another location where things were not growing as well as you would expect. And so we called that the damaged and compared it to the normal, which was our control. And so we looked at pH, sodium concentration, exchangeable sodium percentage, and soluble source index. And so the way that we're not going to read through this and go into details, it takes us a while to go through what all these things mean. But the more salts you have, right, the higher these numbers will be, like sodium or exchangeable sodium percentage or soluble salts index. So you don't want those numbers to be really high. And so if you just compare, normal and damage, right, for sodium, normal damage is really high compared to the normal. Exchangeable sodium percentage, normal is low, damage is high. Soluble salt index, normal is low, damage is high. And for soluble salts index is exceedingly high for the damaged. And so the shallow is relatively higher in terms of the numbers than the deeper. So suggesting that, you've got this very thin layer within the 0 to 6 inch depth range of the soil where you've got prominent localization of these salts. And so ultimately, when you look at these numbers, you read them within sort of a sphere or some fields. And then depending on what numbers you get, right, then you can get a conclusion such as this, which is that for this particular site, there's severe impacts on plants as a consequence of the salt content. And so here's, some actual numbers that we have, that there's high salt content in the soil. All right, so that's the soil. But then again, I'm a hydrogeologist, right? And so what about, water resources? And so one of the things that we could do was we could also compare surface water bodies in terms of water quality. So there was a data set that we had access to where there were samples collected from 2 creeks. And this is again in Hyde County. There was Rattlesnake Creek and Meadow Creek. And so the first sample set was collected in 1984, 1985. And so we went back to exactly the same locations as those samples were collected in 2018, and then looked at the salinity in those creeks. And so for Meadow Creek, there were 10 samples. And then in 1984, 85, it was 8 plus or minus 2 parts per thousand. Whereas in 2018, it was 16, or about double. And then at Rattlesnake Creek, you had plus or minus 2. And then in 2018, there was 14 plus or minus 2. And so again, some numbers to then indicate what might be going on. So we've looked at the soil. There's a soil problem in terms of salinity. We looked at surface water bodies in terms of these creeks, and then there's been a change in time. So we're able to document that not only is there a high salinity, but then there's also a change that there's been an increase. And so again, some of the questions are, well, what is going on? And so can we come up with some ideas of what may be causing these elevated levels of salts in these agriculture fields? And so what we did, so I involved some of my students in my class, and I'll take my class out, and then we'll look at these fields, and then they'll run a field experiment and so on. And so we said, well, let's just take a step back and just open the playbook. And in the playbook, what can we come up with as potential drivers of what is causing this phenomenon? And so if we open the playbook, one of the things that we can relate these issues to is overwash from storm surge. So if you have a storm and the winds are blowing from a certain direction with a certain strength and magnitude, you'd expect to have all this ocean water or sound water inundating these fields. And so there you go. If the ocean water is salty, and then you have this inundation, as can be shown in these 2 images, right? So here's the field in Hyde County, and the entire field is inundated by storm overwash. And so if that is salty, but then we should expect to have salty conditions. And so there is one mechanism. And so, but then the question that follows that is, well, how long does the salt linger, right? And so in this case, it's going to be a top injection of the salts, right? And what would those dynamics be over time? Do you expect that to stay there for a while, or is it going to dissipate over a short time? And then what might be those time constraints? So what else could we sort of think about in terms of what might cause salinization or saltwater intrusion? And so let's wait to get to my next slide. All right, here we go. So another driver might be sea level rise. And so with sea level rise, the idea is that we have the present day, And so in terms of the present day, you have, I keep on exceeding the slide, excuse me. So on the left-hand side, let's assume that that is present day. And so when we talk about groundwater, groundwater saturates the subsurface. And so if you're looking at an unconfined aquifer, what you'd expect is that the boundary between the groundwater and where there's no groundwater in the upper boundary is the water table. So the line where there's a little triangle underneath the land surface, that is the water table. And that's just the boundary, right, between what's above the groundwater system and what's in the groundwater system. So what's interesting is that that water table is controlled by sea level. And so if you follow that line from the right-hand side of the screen to the left-hand side, that line intersects the sea at a point, more or less, right? For at this scale that we're looking at, it intersects at a point. And so the sea will drive the location of that point. If sea level was to go up, then that point would also move up, right? And that's what is illustrated in the next figure on the right. Whereas you had your original water table, and then when sea level goes up, that water table also rises as a consequence. But then what does this have to do with saltwater intrusion, right? And so this is what it has to do with saltwater intrusion. If you look at the first cartoon on the left, there's a wedge underneath the land surface that comprises seawater. So the seawater percolates into the ground from the ocean, and then it fills this zone that looks like a triangular wedge in the subsurface. And so that is going to be salty. And so the process of saltwater intrusion is where you might have salt water going in areas that were originally fresh. And this is what's going on in the second figure. So look at how big that triangular wedge is in that case. And that is because you have moved the intersection between the water table and the sea upwards and inland. So because it's moved up and in, now you've got a much larger area underneath the subsurface that is now overtaken by seawater. And so in this case, we're saying that there's saltwater intrusion because saltwater has intruded this land or this region, which was originally fresh. And so if you were a farmer that was close to those trees, right? So previously you were far away from that saltwater wedge, and now due to sea level rise, you might have more inundation or the likelihood of more inundation from the actual sea, where the sea can go overland to your farm, or you can have saltwater coming in from the bottom. And so this is kind of like the bottom up approach, whereas with the overwash was a top down approach. And so there's another potential mechanism. So there are a couple other mechanisms as well. And so back in the 70s, 80s, if we look at the North Carolina, Virginia border, there's a large pumping center in Franklin. And what this did was that if you extracted groundwater, when they extracted groundwater of this region, it had the effect of lowering the land surface. So extracting groundwater can lower the land surface. And so that lowering of the land surface might then have an impact on the dynamics in terms of the water resources. And so this might induce a relative sea level rise, right? And so we can say, well, why does pumping leads to saltwater intrusion? Well, in this cartoon, we're showing that you have a well and it's drilled into multiple layers, alternating layers of sand and clay. And if you draw a lot of water out of that system, you might then allow the water to then escape from the clay layers, and then that will compress those clay layers. When those clay layers compress, then on the surface, the manifestation is going to be subsidence. And so if that's close to the coastline, that subsidence will induce relative sea level rise. So it will seem as if the sea is rising relative to the land surface, right? And so with that dynamic, then you have sort of like a sea level rise type of scenario that I just described, where then the wedge would move inland and take over regions that were initially fresh. And so that could be another driver. Another mechanism that we can invoke for this movement of salt water into these regions is wind tide events. So several years ago, we did another study south of the area that we're looking at, And what we found there was that if there's a wind that is blowing perhaps from the south with a certain magnitude, that wind would blow over the sound, the Pamlico sound, and it would push salt water into the interior. And then so if you have some creeks or canals or ditches, all that water is going to be moving inland as a consequence of the wind pushing that water northwards. And so you would, in fact, the phenomenon would express itself in that water would be flowing the wrong direction, right? So instead of the water moving to the south, the water would actually be moving northwards in these creeks and canals and ditches. And so why would you have a difference in flow direction? That's because the wind is inducing these wind tides. And so if the water therefore is salty, then you have salty water from the sound, like Pamlico Sound, moving up these ditches and canals and moving into these areas, into these wetlands that you'd expect to be fresh, but now they are inundated by salt water. And so there's another mechanism that we could invoke that would drive saltwater intrusion. And so the title is Saltwater Intrusion / soil salinization, right? So what's the difference in this context? Well, saltwater intrusion is the physical movement of water, whereas with soil salinization is when the soil gets salty, and that could be perhaps due to evaporation. And so if you have a lowering water table, right? So perhaps the water table might be high and then it's low, so it's fluctuating, it's moving up and down. So you might have a consequence where the water table will be under the influence of evapotranspiration. And so some of those salts then will start to concentrate because of where the front is, the intersection of groundwater and fresh water. And so that might lead to an accumulation of salts, perhaps at the land surface or close to the land surface, due to those changes in the water table and evapotranspiration. And so that would then lead to soil salinization. And so you have this perhaps a salt crust that may persist, or just these regions where in the subsurface you have got lots of salts. So in North Carolina, there are thousands of kilometers of artificial channels. And here's a map that I derived from GIS. And so you could see some of these features here that are straight lines, and so all of those are canals or drainage ditches that have been mapped in North Carolina. And so if you have all these wind tide events occurring, or if you have perhaps wind tide, if you have storm surges, so these ditches and canals could facilitate some of that movement of water or salt water inland, further away from the Pamlico Sound or the Albemarle Sound. Okay. So those are some of the things that we had sort of in the playbook. And so we said, well, let's come up with some experiments where we could perhaps capture some of those dynamics. And so again, working with the colleagues from North Carolina State and the cooperative extension, we embarked on a project where we said we would monitor water levels, as well as specific conductivity or salinity in the subsurface, in the soil, and in surface water bodies. We would also sample soil materials, and would also use some geophysical approaches, to get some data from the subsurface. And so here are some of the devices that we use. Here's a Geoprobe electrical resistivity. So we're vertically down and measuring the electrical conductivity of the soil, of the sediment, and then seeing how that electrical conductivity changes with depth. And then we could relate that to whether there's more salt content or less salt content. We use ground penetrating radar. Then we have some other devices where we're monitoring. And so I won't show all the data that we have, but I'll just show you a few data here and there that are most interesting. And then again, some of these data we're still processing and still building a story as to be more conclusive about exactly what is happening. And so when it comes to monitoring stations, so there are different spheres that we could monitor. We could monitor the atmosphere. And so we have weather stations. So there's a weather station in this photo on the left-hand side. So you see the three columns. So those are wells that we drilled at this location. And so close to those wells, we also had a weather station. So we installed a weather station to measure temperature, precipitation, wind direction. So that's in the atmosphere. And then we were recording water levels and conductivity and temperature in the groundwater system at different depths. And then about maybe half a mile up the road from this site, there's this creek. And so then we're also recording temperature, conductivity, and water level in the creek. And then at this very site, which is the Hyde County site, we had 3 clusters. So there's the picture that I showed you is HCO1, so that's the first cluster. Then here's another cluster, and then here's another cluster. And so here's somebody's house, and all of these are agriculture fields. And this area right here, as I showed you, this is the one where you might have had the problem. So when the farmer was growing their crops, this is where they had poor productivity, and then productivity started to extend. And so basically, they don't do a lot with this field. You know, they've gone to that field and to this field. And so for them, that was, you know, their impetus to say, what's going on? And can we try and figure this out so we can solve this problem so we can move on with our lives? So that is the Hyde County site with the 3 monitoring stations. And at each cluster, we had anywhere from 1 to 3 wells. These were installed at different depths, so we can figure out what was happening at the different depths and also try to determine the groundwater flow directions. So cluster 1, for example, had the 3 wells. One was shallow, intermediate, and deep. And then the one that was shallow was about 1 meter deep. And the deep one was almost 3 meters deep. And then we've got the cluster 2 and cluster 3 with the well that was due to about 1.5, and then the other one was to do like 2.5 meters. And so here are some examples of some of the loggers that we're using. On the right-hand side, we've got 2 types of loggers. We've got an activity logger or salinity logger. That's the black one. And then the gold one, that is a water level logger. And so both devices will also give you temperature readings. And so you just deploy these in the wells, and then you let them be, and they stay there in the well for however long you want to leave them there for. And then they're recording the parameters, either temperature, conductivity, or water level at some interval that you set. So we set this probably at 10 minutes or 15-minute intervals and recording over time. So we come back perhaps 1 month later, right? And then so we have a high resolution reading of what's going on in the subsurface. And so this is better than what we did previously, where we just went to surface water bodies, and then we measured what were in those 2 creeks at a certain point in time. And so we're not getting a continuous reading. So in this case, we looked at the groundwater and installed those loggers in the groundwater, and then we're getting a high frequency reading of what's going on in the groundwater. We did the same thing for all the surface water bodies as well, so we can see if we can make any associations between what was happening in the groundwater compared to what was happening in the surface water. And so we didn't want to miss anything between the atmosphere and the groundwater. So remember that when I was showing you the other figure with the water table, so the water table is going to be some distance below the ground surface. Well, how are you going to measure the dynamics between the water table and the land surface? And so to do that, we then acquired these soil moisture sensors that we deployed at 3 depths, 1 inch, 2 inch, and 1 foot, 2 feet, and 3 feet depths. And then there's another one that we then installed at maybe 3-4 inches depth, because again, when we were talking to soil scientists, said, why did you put them at 1 foot, 2 feet, and 3 feet? All the action is within 1 foot, right? And so they had to go back and then install another sensor within that 0 to 6 inch interval that they were really interested in. So these soil moisture sensors record soil moisture, soil temperature, and soil conductivity. And so when we're designing this experiment, we're thinking, could we see a front sort of moving, right? So the question is it top down or bottom up? And so if it's top down, then what you might expect to see is that, for example, during a storm surge event, you have this saltwater front that will start from the surface, and then to progressively go deeper into the subsurface. And so your logger should be able to pick up that progression. At least that's what we thought. Or if you have evapotranspiration occurring, and then you've got this front that is moving from the bottom going up, could you then pick up those changes with the soil conductivity over time? So that was our thinking in terms of our design. All right, and so I'm going to zoom through some of these really quickly. So this is just really showing what we did at the Camden site. Again, 3 points for groundwater monitoring, and then 1 point for surface water. And for all the sites, we had 3 points because in the groundwater world, you can't determine the direction of groundwater flow with just one well. You can't determine the direction of groundwater flow with just 2 wells. You need a minimum of 3 wells. So at each site, we had 3 groundwater wells in the same unit, and then so that we could try and figure out in which way the groundwater was moving. And so at this particular site in Camden County, you can clearly see you've got these drainage ditches, and then there's also another ditch, a much bigger ditch that extends out of a photo that we suspected was bringing salt water in if you had winds blowing from a certain direction. And I'll show you some of those results in a minute. So another site, Pascotank site, again, 3 groundwater wells, 1, 2, 3, and then we also had a steering well in the canal a mile away. So we had another ditch right there next to the Pascotank County well site number 2, but then that ditch, would run dry and would have no water in it. And so we needed something more consistent. So we installed another steering well to monitor conductivity, temperature, and water level in the ditch that was almost all, it ran the entire year. So 3 sites with at least 3 groundwater monitoring wells and surface water monitoring wells, as well as soil moisture and conductivity, and then also ran some geophysics at all the 3 sites. So I just wanted to show this just for context when we're talking about what's fresh water, what is saline water, and what is highly saline water. So this is from the USGS. Anything less than 1 ppt, where ppt is part per thousand. So anything that's less than 1 part per thousand is fresh water. Anything between 1 and 3 is saline water. And then anything between 3 and 10 is moderately saline. And anything above 10 to 35 ppt is highly saline. To cut to the chase, most of the values that you're going to see will be in this range, right? 1 to 3 pp, 1 to 10. So from slightly saline to moderately saline. And perhaps some fresh, where we have some background. So run a bunch of tests, geophysics, groundwater monitoring, surface water monitoring. And so here's an interesting result that we got. So this is from Hyde County. And so what we have here, I'm showing the salinity, and this is in parts per thousand. And then on the x-axis, I'm showing time. And this is in terms of a date. So we started in 2018, and it goes all the way to 2019. And so my students have been collecting additional data, and he's working on his thesis. And so when he's done with that, then we'll have additional data to add to this time series. And so what this graph shows is pretty interesting. And so the lines represent the salinity from 2 sources, that is groundwater and surface water. So the solid lines are groundwater. And so remember I said we've got 3 clusters at Hyde County. And so depending on where you are, you've got a slightly different salinity reading from Hyde County. But it's between 3 and 10, right? So slightly saline to moderately saline for all the groundwater wells. And what's also interesting about the groundwater salinity is that it's more or less consistent over time, right? So whether you are in deep, shallow, cluster 1, cluster 2, there's this consistency in the readings of the salinity. If you look at the surface water body, however, right, which is this sort of maroon colored line, there's a lot of variability. It goes up and down, up and down. In some cases, it's fresh, it's below 1 ppt. And in some cases, it's above 15 ppt, right? So pretty high compared to groundwater. So groundwater is kind of steady, but it's saline, right? Whereas fresh water, usually it's saline, but sometimes it goes to fresh. So all this variability. And so this got us thinking. Again, we're trying to figure out, well, what's the mechanism? How do we get to have these salts going into these agricultural fields? And so could it be that you have got saline water and surface water bodies that then go into the groundwater system? Well, it turns out that groundwater and surface water interact. And sometimes the interaction is in one way, and then in other cases, the interaction is another way. So how can we determine that? So we look at water levels. And so in this graph, I'm showing water levels from groundwater wells. So again, these solid lines, red, blue, and green, these are groundwater levels. So y-axis is water level, and then again, x is time, and we're showing time in terms of the date. And so this maroon line here, that is the surface water body. And so what we can decipher from this is that if the water levels are high in groundwater systems compared to surface water, then water moves from the groundwater system to the surface water body. If the water levels are high, let me do this with an example, right? Like where there's this arrow right there. So if water levels are high in the surface water body right there, compared to groundwater, which is this, then you expect surface water to be moving from the surface water body to the groundwater body. And so what this suggests is that you might have this flip, where in some cases, water is moving from surface water to groundwater, and then you have a flip, then it's moving from groundwater to surface water, and so on. And so the question here is, could you have an instance where the water in the surface water body is moving to the groundwater system, but then at the same time, it is salty, right? So if that's the case, then we could infer that that's the period in time of the interval where you have groundwater surface water interactions, where surface water is going to the groundwater and making the groundwater salty. And so this is where the arrow is highlighting when that might be happening. But as we show that there might be that dynamic occurring at that particular time due to the changes in water levels. And then in this case, at this point, you might have high salinities in the surface water, and then who knows what's going on in the groundwater. So if that point was next to this green line, to the groundwater well where this green line is, you wouldn't expect there to be a significant impact, because the groundwater is more salty than the salt water. But then if you had an instance where you've got perhaps that surface water close to this groundwater well, maybe you might expect to see some interaction there. And so having said that, we don't really see sort of like a blip in any of these groundwater wells as a consequence of that interaction. And so there are several reasons why that might be the case. One is that, well, if I was to go back, that dynamic where if it's the surface water body, right? So it's a losing stream at this stage, it's losing water, and then it switches to a gaining stream, right? So that interval, it might just last a few days. And so it might not be sufficient time for that front again to make its way all the way to the groundwater system, depending on the distance between the well location and the surface water body. So as I said earlier, the surface water body that we're recording these salinity readings was about maybe half a mile to a mile up the road, because we didn't have a surface water body close to where we were. And so again, this is just inference. Because the ditch that we had initially indicated as a good site in which we could measure the surface water bodies, it ran dry, after about a month. And so we didn't have a consistent reading from that to then make any really good associations. If we had those data, then it would be almost definitive. But then that didn't work out. And so we had to go to a backup, which was about half a mile away. And so here we're just inferring. So that is what might be happening in this case. But again, there's a potential. Well, what we can definitely say is that you have changes in surface water bodies. So these surface water bodies are definitely a conduit for salt water, because they should be fresh, right? But then they should be down here, but then they are not, right? And it's a creek. So we expect it to be fresh, but yet why isn't it fresh? So you might have these wind tide events that are driving water up into the creek. And then when they dissipate, then the water goes back to fresh, and so on and so forth. So the surface water bodies, creeks and ditches definitely, again, play a role in bringing the surface, the salinity inland. But then the question is then, how is that dynamic occurring when that water is inland? Do we have any evidence from storm surge? And so I don't know if we're lucky or not. We had 2 hurricanes hit. We had Hurricane Florence in 2018, and then we had Hurricane Dorian in 2019. And so with Hurricane Florence, we had instrumented our wells with automated water level loggers. So we don't have any data in terms of high resolution time series data. what we had is one of our collaborators, an extension officer, Andrea, she just went out to the field site and said, hey, you remember the field where we saw the wells? I was like, yeah, well, it's flooded with water. I'm like, well, go ahead. And if it's safe, right, go ahead and take a measurement and see what the salinity is like. So she went out there, and then this is the salinity that she acquired. So she took a photo and said, here's the field, and it's 10.7. So you have overwash from Hurricane Florence, and it's moderately saline. And so again, where is this water going to go, right? It's going to go into the field. So again, definitively, there it is in terms of a trigger or a source. But then where does it go once it dissipates into the subsurface? Does it stay there? Does it move? And then how long does it linger? We had then another hurricane, and so I was pretty excited. But then in this particular case, when we had Hurricane Dorian, the flooding was not necessarily from storm surge, it was just from precipitation. And so the reading for this one was fresh, right? So we didn't really get to run our experiment. So I was excited for this hurricane event because then we had instrumented the site, and then we're going to get high resolution data. But then lo and behold, there was no storm surge, there was just flooding from precipitation. In any case, well, with this data, that we can definitely say that if you have storm surge, right, we took a measurement and it was moderately saline. So there is another source where this water might be coming from. So in Camden County, I won't show a bunch of data from Camden. I'll just show this one because I think it's interesting. So this kind of yellow line that represents the salinity in the surface water body. And I'm just indicating the 1 ppt threshold right there. And so again, this is salinity and this is time. And then these other ones are groundwater salinity levels. So there's one interval, right, from 1027 to 1216, maybe two months or so, where the salinity in the ditch or the canal was higher than 1 ppt. Other than that, it was fresh. And so why might this be the case? And again, this is a ditch. And so we were surmising that it might be, again, this wind tide phenomenon that are occurring. And then after that, then it went back to normal. And in some cases, we're not getting a reading. Perhaps the water level went really low, that we couldn't even get any water into the canal. And so we're not getting any measurable reading from the device. And so in this case, the question then is, well, what's going on at the field site? Do you have water overpouring onto the field, or is the field still dry? And so just to refresh your memory, so here's counting. So we've got 3 groundwater wells, 1, 2, 3. And then on the left-hand side is a steering well. And so there's that canal/ditch. And then we definitely have these ditches that just end in the middle of the field. And so if that water moves all the way up to the ditch and then makes its way into the field, then you will have problems with salinization or saltwater intrusion. And so I'll skip over the water levels and talk about what was observed at some point. So this is a picture showing that there's this ditch. So there's a ditch over the top of the picture with a bit of green. And then where I've got my measuring tape, that is where basically that's the field. And so in this case, you've got water overflowing into the field. And if that water is going to be salty, then again, there's your source. So it just depends on the dynamics. And then again, we're using the groundwater levels, the water levels to figure out those dynamics where you might have an event such as this, where you definitely see that there is overflow from that ditch. And then if that water is salty, then for this particular farmer, that might be the mechanism. Otherwise, for this field, there's no other issues that we had seen other than this overflowing of water that led to poor yield in his field. And so the driver there might be wind tides, right, as a mechanism. Pasquotank County, so this one is interesting in that this is what you'd expect of a normal field without any problems. So again, here's the 1 ppt threshold, and so salinity and time. And so we've got groundwater and surface water. So all the recordings that we did for groundwater and surface water, that's Pasco County, they were fresh, right? Groundwater, well 1, well 2, well 3, fresh. You go to surface water, fresh. And so, well, this is what we expect, but the farmer is telling us that we've got problems in the field and not getting sufficient crop yield. And so what we did then was, so here's a sketch of that field site. So top right, that's where there's one well. Bottom right is another well, and then on the left is another well. But then between wells 1 and 2, we ran a Geoprobe, which is a device that you use to determine electrical conductivity, and use percussion to drill a hole into the ground. And then when you're doing the hole in the ground, you're measuring the characteristics of the sediment and the water as you're doing that. So we went to the red circle, blue square, and green triangle and ran the Geoprobe to see what was going on. Because groundwater said it's okay, you know, surface water, that's okay. But where is the salt in this particular location? And so at the location where you had the circle, sort of in the middle of the field, that's where the farmer had the major problem. And so that's where we put the first groundwater well, we put soil moisture sensors there, and that's where we also put that's where we ran the first Geoprobe. And so what this tells us is that within the first, this is in meters. So you've got depth in meters and electrical conductivity. So the Geoprobe doesn't give you salinity, but it gives you electrical conductivity, which is, we're using it as a proxy for conductivity, for salinity. The more conductive, the more saline we expect that sediment to be. And so the salinity or the conductivity could be a function of the material properties and or the presence of conducting fluids, in this case, salt water. And so for this farmer, at that location, he had a patch that was problematic. And so when we ran the Geoprobe, we get a large signal, and then it kind of dies down to some background level. And then as we went further away from that location, so you get a small ping right there, and then it goes back to background. And then the one that's near the ditch, it's basically background. And so with the soil scientists, what we did is we took, again, soil samples from those locations. And then what this has been interpreted to be is that this is a salt crust. And so at this location, you've got this salt crust that was picked up by the Geoprobe, and then there were no crops that were growing there. And then as you go further away from the ditch, right, then you have basically background normal conditions. And this doesn't persist for a large section in the subsurface. It only goes to perhaps, if anything, maybe 2 or 3 meters, and then that's it. This one, basically background, that one background. So again, all these questions. So groundwater is fresh, surface water fresh, but yet you have this spike. And so where is that coming from? And so some of these are sort of the unknowns that we're still working on. All right, we talked about that. Then I think I'll just show one more. So we also looked at Hurricane Dorian in Pasco County, because in High County, we only had precipitation, whereas in Pasco County, there was a little bit of a storm surge. And so we instrumented here in the Albemarle. And so we had some water levels in the Albemarle. And then we also were looking at what was going on in the groundwater system at Pasco County. And so this arrow shows when we had Hurricane Dorian, and then it wasn't clear, because again, there was a hurricane, so you couldn't run out there as a scientist and see what was going on. So you talk to the farmer and say, what happened on the day? Did you see any flooding? And then based on that discussion, it wasn't clear whether it was inundation from precipitation or inundation from storm surge, at the field site. But then at least we had some data from a pier that was actually in the Albemarle Sound. So this arrow shows where that happened, but then you also see water levels rising. And again, that's indicative that that's being driven by the hurricane. And what we really want to look at was then the conductivity or the salinity. And so this black line is the one that shows what was going on at the pier. So there was a bit of a blip right there at the pier, which you'd expect. So you'd have more salt water being pushed to this location. But then our question was, well, could that then propagate inland? And so maybe there's that, going up there, but again, it wasn't conclusive. So yes, we did have something from Hurricane Dorian that we can point to, but then we couldn't really definitively say that that is what was causing that increase in conductivity in Pasquotank County. So which kind of leaves us with perhaps it's evaporation or evapotranspiration, that you have now soil salinization in Pasquotank County. So we're not necessarily talking about bottom up or up down processes at that location, but maybe it's soil salinization from evapotranspiration. So so to wind down, so this is ongoing, and so what we've found is that groundwater is moderately salty, particularly in Hyde County. And if you go to Camden and Pasquotank, groundwater is fresh there. In some cases, the surface water is kind of the culprit in that it's going to be saline. Most of the water in Hyde County is saline. The creek that's next to the field site is saline, and then other creeks that we looked at are saline. And over time, we documented that those levels have gone up. And so there's a potential culprit there. And moving forward, we are going to continue monitoring and trying to build a better picture. But the evidence that we have so far suggests that the drainage ditches and the canals may be facilitating saltwater intrusion. There's also evidence that storm surge might facilitate saltwater intrusion. We are looking at revising some of our techniques in terms of what we're monitoring, and also using some more geophysics. And so the next talk that I'll probably give, will include a large proportion of geophysics, because then we're thinking about what about the characteristics and the texture. Might you have paleo channels that might be enhancing some of the regions so that they are more susceptible to soil salinization and so on. So we're using geophysics to try and answer those questions. And so part of the process is in the graduate student's hands. And so once he gets that done, then we'll have some really interesting results to talk about. But as of now, definitely some evidence that drainage ditches and canals are impacting saltwater intrusion, as well as storm surge events. And so with that, I'd like to acknowledge the National Science Foundation that funded some of this project. We also got some funds from the North Carolina State University GO grant. Students from East Carolina University helped out with data collection. And of course, this wouldn't have been possible without all the folks from the North Carolina Cooperative Extension at North Carolina State University, Carl Crozier, Dana Rashash, Andrea Gibbs, Wood, Dustin Wood. And then also would like to acknowledge Brian Lannon, who's a soil and water conservation specialist in Camden County. And with that, I will be glad to take some questions. Thank you.
Thank you very much, Alex. Time for questions.
I have a question about how you were using GPR. So if my knowledge serves me correctly, GPR doesn't give a clear signal in salty soil. So were you looking for that absence of a signal to indicate where there was a saltwater intrusion?
Exactly, yes. And so if it was going to work, right, then we say, well, let's kind of figure out what's in the subsurface, right, and see, how we can characterize the subsurface. If it wasn't going to work, we're like, well, it's not working because it's salty. And so, yeah, that was our approach to try and figure out what was going on. Yeah.
Thank you.
Hey, Alex, I have a question. Can you speak about the impacts on the farmers' fields that they were noticing? You showed some pictures of isolated areas that had been impacted, but it seems like based on some of what you've shown and some of the data that I would expect it to be very widespread, unless it's just related to minor soil characteristic differences. I don't know. Can you just speak more about that?
Right. And so there's actually been some work that has been done. There's some folks that also try to use remote sensing technology to try and pinpoint and then ground truth some of those areas that were pinpointed to see what was going on. And so there's kind of like measles type of phenomenon going on, which is, even from my perspective, which is very interesting, right? Because even for that one field in Hyde County, the whole field is inundated with salt water, but yet you only have this one patch that's problematic. And so with a lot of what has been documented, you have this kind of measles type of phenomenon where it's not necessarily an entire region that is impacted, but then you have something going on here, then there's nothing there, even within the same field. So, which is a really interesting question. And that's what we're thinking. Let's now look at the structure or the texture or some of the features in the subsurface, and let's use some other geophysical techniques to try and capture what's going on in the subsurface so we can see what is different within that small localized area. And so, yeah, with the farmers, they do get a lot of that where it's localized. And then some of their solutions will be, well, just put gypsum in those locations so that then you can remove the salts, but then you leave the gypsum there as a consequence. So, but then that's very costly. And so one of the questions that we had, though, just from the get-go was, well, if we know what is really causing it, then even some of the remediation that we might do might be aligned with what's going on, so that things are dealt with appropriately. But yeah, so it's kind of a mishmash when you look at the expression of the phenomenon.
Yeah, thanks.
Hi, Alex. I'm Linda. Thank you for that
Hello.
talk. I appreciate it. So I've been to North Carolina so many times and a lot of farmland. Just wondering a way of, talked about the gypsum. I was just thinking about there's an awful lot of irrigation farming. So bringing the fresh water from above and having it filter through, is that a way to remove or alleviate the problem areas? And I guess that's maybe an area of research, but I'd like your comment on that.
Right. And so that's one of the problems for some of the farmers that we're talking to, is that they don't have access to irrigation. So in some places, yes, you can irrigate or can just flood the land. But then the ones that we instrumented and then some of the ones that we had conversations with over, they don't have that luxury of actually irrigating their land. So they're relying on precipitation. And so, yeah, if you do have gypsum, then you have to flush all of that out, and then they don't have that mechanism. So on one hand, yes, it could help you, but then on the other hand, you need that flushing mechanism to actually get to where you want to go.
All right, any other questions for Alex? All right, let's thank him one more time.
Yeah, thank you.